They don't flow like water, they don't roll like marbles. But every hour, millions of grains descend through steel chutes, spiral inside augers, and travel across ports and continents, as if they were part of a liquid system, dry but fluid. In the world of agricultural logistics, grain isn't just a crop, it's a material in motion. Engineers don't treat it like produce. They treat it like flowable mass, a bulk substance governed by physical laws of angle, pressure, density, and friction. And at the center of this motion lies a paradox. The faster you move it, the more you risk breaking it. Grain behaves like what specialists call a granular fluid. It's not exactly solid, not exactly liquid, but subject to flow dynamics that combine both. Unlike water, which conforms instantly, grain flow must be engineered, using hoppers, feeders, and chutes designed with millimeter precision. The grain's surface texture, the chute slope, and even the ambient humidity affect how smoothly corn, wheat, or soybeans will fall. In this choreography of movement, the key isn't just speed, it's control. Flow rate must be optimized to prevent bottlenecks, but also to reduce wear. The smoother the flow, the less the abrasion. The less the abrasion, the higher the survival rate per kernel. Each adjustment to velocity or slope isn't arbitrary. It's a calculation designed to move billions, one intact unit at a time. Think of a pneumatic conveyor system in a high-tech warehouse. Parcels ride air pressure through translucent tubes, each bend controlled to prevent collisions or slowdowns. Now imagine a similar system. But instead of parcels, imagine 5,000 tons of barley. Instead of sealed boxes, a cascade of uneven organic particles. And instead of a climate-controlled facility, imagine the unpredictable world of a grain port. Here, engineers use suction, airflow regulation, and angular correction to preserve the grain's physical structure, not just move it. Because in bulk agriculture, fragmentation is loss. And friction, if left unmanaged, becomes invisible damage. This story begins long before automation. Grain elevators along the Mississippi River, towering silos of concrete and steel, were early temples of agricultural logistics. They borrowed principles from mining, conveyor belts built to move ore, gravity-fed systems that loaded barges without a single powered arm. The choreography was mechanical, but elegant, guided by a deeper logic. Grain moved downward, with gravity. It spread laterally through controlled gates. What miners learned hauling crushed rock, grain handlers adapted to protect food. The scale was immense, but it was also silent. That's the genius of agricultural engineering. It's never loud. It just moves. And yet, movement alone isn't enough. Material science enters the equation, often unnoticed. The augers that twist grain into trucks and ships are forged from steel, but not just any steel. The hardness of the alloy, the angle of its blade, and its surface friction coefficient all determine how much damage is done in transit. Over months of operation, poorly chosen materials create micro-wear. That wear generates friction. Friction becomes heat. And heat, over time, cracks the grain. Engineers must calculate beyond the machine. They must think about the cargo's fragility, not just the motor's power. Globally, the numbers are staggering. The 10 largest grain ports handle a combined flow of over 45 million metric tons per day. To visualize that, imagine the daily throughput of the world's major petroleum pipelines. Now replace liquid fuel with dry maize, soy, barley, rice. These aren't just ports. They're agricultural superhighways, each with automated loaders, real-time weight sensors, silo pressure monitors, and anti-friction liners in their conduits. Every part designed not just to move grain, but to protect it. Grain, after all, is not static. It's not just harvested and sold. It's moved. And in that movement lies an entire universe of engineering. The universe where every kernel matters, where each auger turn, each slope angle, each airflow valve is a decision between efficiency and loss. Between feeding the world and letting a portion of it fall through the cracks. Inside a grain handling system, the auger seems like a simple mechanism, a spiral blade inside a pipe, powered by a rotating shaft. But when you're moving soybeans by the ton, simplicity becomes illusion. What looks like a basic rotation is, in truth, a delicate balance between torque, resistance, and grain integrity. 1 degree of misalignment, one variation in RPM, and the auger transforms from transport tool to mechanical grinder. That's how thousands of tons of grain are quietly destroyed, not in storms or accidents, but within the very machines meant to move them. Friction is the silent culprit. When an auger turns too fast or is improperly aligned with the feed angle, the friction between metal and kernel increases, and with it, heat. Soybeans, for instance, have a thin protective hull that shields the oil-rich center. That hull becomes fragile under excess temperature and pressure. Within seconds, micro cracks appear. Within minutes, fragmentation begins. And what was once market-grade cargo becomes downgraded stock, or worse, waste. These losses rarely make headlines, but they echo through the supply chain in the form of spoilage, mold risk, and reduced nutritional value. Modern systems are no longer blind to this. Torque sensors embedded in auger drives now monitor real-time resistance, identifying spikes that signal material overload or mechanical stress. RPM feedback loops adjust rotational speed to match the grain's physical behavior, slowing slightly when soybeans are too dry, accelerating gently when corn density is stable. This isn't guesswork. It's algorithmic response. The auger no longer just turns, it listens, adapts, and preserves, and the results are measurable. In a USDA-monitored pilot, reducing auger speed by just 12% during soybean transport led to a 40% drop in broken grain counts. That's not a marginal gain, that's a structural correction, a performance leap rooted not in redesign, but in rethinking priorities. More speed doesn't mean more efficiency, it often means more damage. The true metric isn't how quickly grain reaches the end of the pipe, it's how much of it arrives whole. In Brazil, one agricultural cooperative took this principle further. They integrated torque-responsive automation into their maize handling line, covering both loading and transfer. By recalibrating speed based on resistance readings, they not only cut waste by 17% in a single harvest season, they extended equipment life and reduced energy consumption, less damage, less downtime, less loss. It wasn't a miracle upgrade. It was precision applied to something long overlooked. This is the paradox at the heart of grain logistics. The hardest part isn't building machines that move faster, it's building systems that move smarter. The auger, often dismissed as a background actor in the agricultural theater, is actually a high-stakes interface between machine and biology. One miscalculation in torque, one overlooked alignment, and the system becomes its own enemy, which raises a deeper engineering question. What is efficiency, really? Is it the number of tons moved per hour, or the number of intact units preserved per movement cycle? In modern agrologistics, survival has become a more valuable metric than speed, because the grain that arrives unbroken isn't just product, it's proof of intelligent design. Air isn't free. To the naked eye, pneumatic grain systems are elegant. Tubes, hoppers, and motors connected in seamless choreography. Grain appears to glide effortlessly, suspended in airflow, moving with a silence that belies the turbulence within. But what makes these systems work, or fail, isn't the visible machinery. It's the pressure balance hidden inside the pipe. Grain isn't weightless, it's mass in motion. And when suction, humidity, or density isn't compensated, flow doesn't just slow, it stalls, collapses, and cracks the cargo from the inside. Unlike conveyor belts, pneumatic systems don't push, they pull. Fans generate negative pressure, drawing grain through ducts as if siphoning water through a straw. But unlike water, grain doesn't conform. It resists, it clumps, it shifts weight unevenly. And when that happens mid-transport, even a slight atmospheric imbalance, A drop in pressure, a spike in humidity, is enough to create turbulence. Suction weakens, kernels collide, intermittent flow begins. What should be a continuous motion turns jerky, and the grain suffers impact injuries invisible until storage. This is where atmospheric compensation engineering enters. Using principles borrowed from aerospace, modern systems now employ adaptive Venturi valves, devices that regulate airspeed, not with brute force, but with feedback. As grain enters the system, sensors detect particle density, moisture content, and flow resistance. The valve narrows or expands accordingly, creating a consistent velocity field. In essence, the system breathes with the material, adjusting in real time to keep flow smooth, centered, and intact. The results are striking. In Kansas, a controlled study tested traditional fixed-pressure pneumatic lines against smart air-regulated systems. The difference? A 28% increase in throughput, and a significant drop in fractured kernels. The same machinery, the same grain. The only variable was atmospheric compensation. Grain didn't move faster, it moved better. In Japan, one grain processing facility operating near coastal humidity zones faced constant flow disruptions. Moisture caused clumping and lag. By integrating humidity sensors into their airflow control system and using adaptive intake modules, they not only increased their processing capacity by 22%, they cut system shutdowns by almost half, not by redesigning the facility, but by rethinking airflow itself. Pneumatic transport isn't just about suction, it's about continuity, and continuity is fragile. Grain doesn't ask for speed, it asks for stability. If the pressure drops too quickly, if the airflow doesn't align with the material's changing density, motion breaks, and with it, the logic of the entire system. The irony is that air, the very element meant to protect the grain from mechanical trauma, becomes a source of damage when not properly calibrated. It's a reminder that in logistics, efficiency isn't about force, it's about harmony. Just as a wind tunnel must be perfectly balanced to test a wing, a pneumatic grain system must be symphonically tuned to its cargo. Because in the end, the grain that arrives smoothly, unbroken, and uninterrupted isn't the one that traveled fastest. It's the one that never had to stop. In a world that glorifies speed, agriculture teaches a different lesson. The logistics of grain aren't governed by how fast a system moves, but by how carefully it handles mass over time. The true race isn't against the clock, it's against friction, fragmentation, and waste. That's why the most advanced grain systems today are no longer calibrated for maximum velocity. They're engineered for density, for the optimized movement of material in bulk, with as little loss, damage, and interruption as possible. Volumetric efficiency has become the hidden metric behind successful grain logistics. It is the measure not just of what is moved, but of what is preserved. Imagine two identical auger systems, each moving 20 tons per hour. On paper, the performance appears equal, but if one system breaks 8% of the grain during transport, while the other preserves 99% intact, the comparison collapses. The system with lower mechanical stress, less fragmentation, and reduced spoilage isn't just better, it's economically and nutritionally superior. Efficiency today is no longer a linear equation. It is a balance of volume, integrity, and continuity. This is where engineering reaches a philosophical threshold. Grain systems are no longer designed simply to transport. They are designed to protect. Every pipe bend, every chute angle, every blade pitch is the result of simulation, field data, and materials testing. Even the internal coatings of grain elevators now use abrasion-resistant polymers that reduce kernel damage during descent. Pneumatic flow regulators are tuned not just to maintain suction, but to modulate velocity based on moisture, air density, and cargo fragility. These aren't ornamental upgrades. They are survival mechanisms for the grain itself. At the port of Santos in Brazil, this principle has become infrastructure. By integrating modular loading arms with adaptive geometry, the port has redefined how density is managed at scale. These arms pivot in real time based on grain load distribution, shifting angles and flow rates to keep cargo steady and uninterrupted. The effect is immediate: less spillage, less air dispersion, and dramatically lower losses at the moment of transfer. What looks like a mechanical arm is, in truth, a fluid instrument, reacting to pressure and mass with the same precision as an automated surgical tool. But the story goes deeper than machines. Designing for density means rethinking what productivity means. It shifts the mindset from how many trucks we can load per hour to how much usable cargo survives each transfer, because spoilage doesn't just reduce profits. It increases emissions, wastes land, and undermines food security. In this sense, every intact grain is a silent victory, the result of foresight, engineering, and respect for the invisible journey food takes before it reaches a table. This is the quiet truth behind 1.5 billion grains moved each day. They are not merely shipped. They are engineered into motion. They are measured, protected, and guided with care. And the systems that move them, silos, augers, conveyors, ports, operate not at the mercy of speed, but in the service of density. In preserving volume, we preserve value. Not just agricultural value, but human value. The guarantee that what is harvested feeds more, wastes less, and honors the intelligence behind every mechanical decision.